second speaker, Pratim Biswas, to give his talk on synthesis of nanomaterials to enable nanotechnology studies, identification and role of various metrics.
Hey, thank you. And it's difficult when you come towards the end, and there have been several excellent presentations. So some of this would be, how do you get this? Okay. Duplicated. Okay, now that we've got my talk, you'll have to bear with me. And as I said, I'll sort of reinforce some of things that you've already heard. I'm an aerosol scientist, so I take some of these principles and use it to synthesize materials. So you'll get a flavor of that, and hopefully we are an enabler, not only of the field of nanotechnology itself, but maybe also to support some of these different studies. Now, before I thought we start, I would just walk you through the day, right? It's impacting us everywhere and all the time. So you woke up in the morning, you had slept on sheets which were impacted by nanotechnology, nice and soft, stain-free, additives. Then you showered with nanotech shampoo and soap. You might have put up makeup and pants that are made of nanotech fabrics. You opened your fridge, you drank milk. Those of you who are staying in the inn across the street, if you look at your, there's no milk available to us, but powdered sort of white powder, and you look at it, at the back it says titanium dioxide as the last ingredient. We are visiting Notre Dame. Yesterday, Prashant Kamat was introducing some of the speakers on his website. There's a video on donuts. He takes a donut, bakes off all the useful stuff, the sugar and things like that, and is left with TiO2, and he uses that nano TiO2 to actually make a solar cell, right? So it tells you these things are all over the place, right? Then, of course, the word is misused, at least a few years back. If you come from parts of India, there is a car called Tata Nano. You can buy it for $2,000 and drive it all around. You could also buy a nano iPod and listen to music. Probably very little to do with nano. Actually, things have reversed now. People don't want to use the word nano, maybe because of the concerns about environmental health and safety. So it goes both ways. And then at School of Work, we are using a computer based on nanotech chips. If you are really a fancy ventilation system or a filtration system, we heard about silver. These could be used to clean up water, clean air. And then you come home in the evening and you're watching a TV, you're playing video games, all impacted by nanotechnology, chips that are made and are becoming more and more effective. And then finally, you have to bear with me and you come to listen to another nanotech lecture. Okay, so with that, here's my outline. I'm going to tell you about the building blocks. Some of this you've already heard, but I don't think it's problematic to repeat it. And I'll try to identify some of the important features and why a holistic evaluation is essential. And then, of course, the main part of the talk where we want to look at controlled synthesis to provide materials. And so what if I can make fancy materials? What is the fate, even while doing let's say, a toxicological test? And I'll try to identify that. And we all work in labs where we make these things. Are our labs safe in the first place itself? You know, I want my graduate students to be very safe. And how do we use this as a model itself? And a lot of things to learn and guidelines to be developed, which we really need to share. So I'll give you a quick overview of all these topics. Some of it you probably are very familiar with. We know that if I have a foot rule, and if the earth is the size of about 1 foot, then a soccer ball that I'm kicking around, of course, this is the year of the World Cup, so good to say, use the soccer ball example, the ratio. So you can see, now sometimes this is difficult to imagine, so I like to put up a human hair. You feel it on your head, and it's about 50 micrometers. Of course, it varies. It could be 50 to 100 micrometers in diameter, and you can fit 2,500 titanium dioxide particles. This is maybe a Degussa nanoparticle. You can fit it onto just the cross-section of this human hair. We are making chips. I mentioned nanotechnology impacting electronics. Chips are becoming smaller and smaller. These are actual devices, and I can fit 250 of them, just the thickness of a hair. Viruses and bacteria are larger and so forth. So it gives you a sort of perspective on size. And the other thing you heard also is most of the molecules, if these are molecules that make up a particle, or atoms if it's an elemental particle, they tend to reside on the surface. And of course, molecules could be different dimensions. These are a diameter of a molecule, again, representative dimensions in nanometers. If I have a 0.1, this is 1 angstrom molecule in a 1 nanometer size particle, close to 50% of all the molecules are on the surface. Very important, because these are going to interact with different surroundings. This is what makes it exciting. And if quantum effects kick in, I can begin to have different types of properties maybe, and I can have functional materials that I can put to different applications. So that's one, and very easily calculated by simple formula like this. And you can see if it's a larger molecule, then close to everything is on the surface of a very tiny nanoparticle. And as you go larger, this is where the US EPA ambient particulate standard is today. You can see a very small fraction is on the surface of the particles. Particles are everywhere. We heard this too, coming out from the smokestack, diesel exhaust, also being formed in the atmosphere, settling down, getting into water bodies. So all kinds of things. These have been, we heard a very nice talk on the geological aspect of nanomaterials. These may not be geological timescale, but still have been around for a very, very long time, and people have studied these very extensively, and there is some understanding as to the impacts of these maybe on human beings. So just very quickly, of course, combustion sources. Any combustion source will be giving out a lot of nanomaterials. Why don't I control the emissions? Yes, we do, but nanoparticles are very difficult to charge effectively and trap, so a small fraction always gets out. And of course, we are driving around in our cars, which also have combustion devices. The sun is an energetic resource. I might emit molecules or gases into the atmosphere. These could nucleate and form secondary nanomaterials. So this is also very important and well studied. And of course, they are naturally occurring. If you are a sufferant of allergies, there are protein fragments which you can inhale. These are also tiny. Of course, viruses, you can catch a cold and the flu. These are naturally occurring to some degree in an occupational environment. If you're trying to make nanomaterials, there's a potential for exposure. So all of this could be put together in the system, and the bottom line is these are all over the place. So we've heard many of these questions. The key, of course, should we be concerned? Do we repeat the mistakes that the chemical industry did in the past? And how do we ensure the safety? Can I make nanomaterials to be safe? And I'll try to allude to that. So I feel that we need to look at the system holistically. Of course, the driver might be an application. Both these applications have been mentioned, even tires very extensively, but it starts right from a synthesis process, maybe an occupational environment. You want to trap these particles. If they are harmful also, we want to trap them. If they are useful, of course, I want to put them to use, so I want to collect them. Then comes the issue of handling. It's not only collecting it right here, I have to really handle them and go and make a product. So there's the aspect of handling and processing, and then eventual use of the final product that we make. And all these, of course, relate to exposure, and you could release to the environment if you can't trap all of this. So there are all these aspects, and a holistic study is, of course, essential. Again, things that we've heard extensively all through. And one can put together charts like this, the entire process now appearing vertically, and at all stages maybe potential for release. But the key is this exposure, right? And of course, if I understand the risk, or maybe even if I don't have a very good understanding of the risk, can I get some feedback to minimize the exposure? So whether something is toxic or not, we really try to minimize the exposure and try to reduce the potential harm. And of course, if I can do a very detailed risk calculation and understand this pathway, we can do some risk minimization kind of approaches to prevent this. But the key is, again, these different aspects that have to be considered. So a few observations. Biological effects of nanomaterials we've heard today are all over the map, and that is not because of a faulty experiment. Each nanoparticle is inherently different. Even the same nanoparticle that I make, now I've picked TiO2, and you'll see a lot of TiO2 in my talk, made by different routes, or maybe even sometimes the same route, could have different biological effects. So these are very tricky materials, and you have also seen a lot of this. Now, one key issue is large number of samples are not readily available. We, of course, heard that we need to have standards and things like that, but these need to be made available. Now, our different labs doing intercomparison tests, we need to begin to do these. In many cases, in other fields, these things have been done where people bring all their tools together at the same place, use certain protocols, and actually intercompare. So this needs to be done, I feel, in the field. And then another question is, what about all the epidemiological data? This is, of course, available now for the ambient atmosphere. It's well known that fine particles are problematic, and you can't say that the ambient aerosol is not complex. It's extremely complex. It's all over the map. It's being transported all over, but there is some understanding, and people are beginning to make some progress. Is there lessons to be learned from that field? Maybe yes, maybe not. And then nanoparticles, they have been made for now decades along, right? People didn't probably call them nanomaterials. We call them fine particles. There has been a chemical industry. Is there any epidemiological data, and of course problematic data, from these manufacturing industries, and lessons to be learned? And sometimes we don't dig back. Now, as I indicated, there are certain materials which have been very problematic, asbestos, silica, and so forth, but is there data available from some of these other industries which are producing these materials now for a long time? So with that, I want to refer to this term. I think Gunther devised this term maybe, or some others. And you go to Google today, there are more than 45,000 entries already, right? So it's a very popular term in that sense, being extensively used. The definition is, of course, listed out there. There are key challenges which I want to point out. One is this issue of metrics, and even the nomenclature. I heard sitting in several talks what nomenclature should be used. There was a talk from our colleague from the medical sciences, and he kept using agglomerate and aggregate interchangeably, and really we need to come up with some terminology which allows us to really understand each other well. And then, of course, eventually the metrics, which was brought out very well, I think, by Patricia. Do I use mass? Most toxicologists use a certain mass concentration, but should it truly be surface area or number or combination or something like that? All of this would be possible if I can really correlate then nanoparticle properties to the biological effects, right? And I'll give you an example. Now, before I start, let's pick TiO2. Some pioneering work done by Oberdoyster. He actually correlated to the surface area this neutrophil production rate, and he used the same nanomaterial, right? And of course, two different sizes, but it correlated quite well to the surface area. Probably a fact that is now well understood, but a good correlation. But then in recent years, you see Warheit, he suggested that it's not dependent on particle size or surface area, and used a different shape of material. Again, not wrong results, but clearly different, and maybe very limited number of samples to maybe come up with some of these conclusions. And you can also see different crystal phases. TiO2 is a very common material. The anatase crystal phase and the rutile crystal phase itself could be very different. And then also a study by Sayes that shows that you could have different effects, but very limited number of samples. So this need for the availability of different amounts of samples is very important, and to maybe do these experiments well and use protocols which are common across the board so that we can duplicate some of these results before we can move along. So I want to address the issue of metrics. We've again heard a lot of this. To us, we form particles. We actually assemble molecules. The bottom-up approach, the molecule is the building block for us. We start with a vapor state. By controlling the temperature history, I can understand the clustering process, which is also referred to as nucleation, and then all kinds of growth processes, and a molecule can then associate with this agglomerate or aggregate, and I'll put those definitions up. There is sintering that can take place. It can collapse into a nice spherical particle. So each of these steps have to be well understood. Then I can go into my lab, design a system where I can control each of these steps and make desired particles of a known size, known shape, known crystal phase, known characteristics. And this allows me to also play and come up with certain desired functionalities. If I want to make the next generation solar cell, can I, knowing what I need here, I try to back calculate and design a process which will give me the material. So one can look at just one of these particles. We call these tiny things the primary particle. You probably heard this also in some previous talks, which makes up what we call a nanoparticle agglomerate. Again, nanoparticle, we saw the definition. In some sense, that's arbitrary, but I can say that each of these primary particles are small, and they are agglomerates. Now, an agglomerate to us is what is a soft agglomerate, which means if I provide sufficient energy, I can break these up and loosen these up and end up with all primary particles, right, which are even not connected in this agglomerate form. In contrast, I can have what we call an aggregate, and this is again terminology. An aggregate is this process where I can really partially sinter this. So each of these are sintered now, and they'll never come apart, never, of course, in reasonable force application terms. These are actually bonded and sintered together, and this is retained. A lot of applications, anytime I want to make a catalyst, I want a very high surface area. I don't want my primary particles to fly out of my catalyst, so I create a hard aggregate. Now, does an aggregate behave the same as an agglomerate? And probably yes, probably not depending on what application I'm looking at and things like that. So at least we have the nomenclature right. And then, of course, we have things like the dimension of the size. How do I characterize something like this? I can use a fractal dimension. I can use a radius of gyration, a mobility size. I bring up mobility size because we design instruments to measure these in flight. I might be interested in the surface area. There are ways now to interpret the surface area by light scattering measurements and all kinds of different measurements. And of course, eventually the shape and maybe the fractal dimension sort of describes the particle shape. So let's go on and see how do I now actually, I'll just walk you through, literally walking through one of our laboratories where we do controlled synthesis. And there are different types of reactors, but just to repeat, we use the gas phase. We like the gas phase techniques because these are scalable. If I really come up with a novel material and I wanted to sort of transfer the knowledge to industry, industry has been doing this. So titanium dioxide is made by a gas phase technique in large quantities. The reactors probably produce tons of material per hour. In our lab, we make maybe a few milligrams every hour, but these could be scaled up to tons per hour, and the steps are exactly what I indicated. And once you understand some of these, you can begin to tailor-make materials. I repeat this, the controlling parameters, how many molecules I bring into my system, the temperature history, because each of these rates are going to be controlled by what temperature history I have, and what's the gradient, and of course the available time. There are many challenges. There's a crystal structure that I would like to control. Of course, the size, the agglomeration, the monodispersity, and I eventually want to make sufficient mass that I can give it out to different people or use these for our own tests. So it's not that we are just making a few particles and being happy with it. We have to produce sufficient amounts so they could be used. So a whole slew of gas phase reactors. Some of these, as I indicated, are already commercialized. These are all research papers. There are plasma reactors, laser ablations, spark discharge, and depending on which reactor we use, there would be some fine-tuning of the properties or some differences between the properties, and one really has to understand these very well before we start using this. I'll talk a little about maybe the first two, or before that, pictorially, a flame reactor is nothing but a flame where I have a fuel, and sometimes the precursor itself acts as the fuel. It reacts here, forms the oxide, and then as the temperature drops, we begin to form tiny particles. I could have different designs, a diffusion flame, premix flame. I'm not going into it. Instead of a flame, I could use a furnace to provide the heat to react the precursor, or a spark aerosol generator where I start with a solid precursor and actually the spark provides sufficient energy to vaporize the material, and then the downstream processes are the same. So there are certain commonalities, and even in the lab, many different components that come into play. And of course, eventually we want to collect the nanomaterials or nanoparticles that are produced. So this is a furnace reactor, and you can see that the flow rates and things like that have to be controlled very precisely, the temperature here, and a lot of these different precursors can be used and things like that. And just to give you an example, this is TiO2, so I can start with a titanium precursor, titanium tetraisopropoxide. It's easy to volatilize and carry it into the reactor, and you can see a nicely aggregated material that has been produced, and this is of course a 100 nanometer bar. I add a small amount of vanadium, and you can clearly see that, of course, the structure looks similar, but the primary particle that I talked about is much greater in this case compared to this. A small amount of vanadium changes the entire particle dynamics towards the downstream side and promotes sintering, and as a result gets me a much larger primary particle. And of course we can tune these. If I want to match it, I can add a very small amount of titanium or vanadium, or reduce the residence time and get the desired materials. But one has to be very careful. If I wanted to just study the effect of vanadium on this, but you can see the primary particle size itself has changed. Flame reactor, very similar. This is a quench ring which allows us to control the temperature gradient. And I want to point out these real-time aerosol instruments. In some sense, at least in the gas phase, our measurement techniques have evolved. Maybe it's a simpler measurement in some sense compared to in aqueous media, but some of these instruments are now very widely available. In flight, I can pull out some particles, place a charge on them very precisely, and classify them by size in an electrical field, and then count them very precisely. This can count down to a single particle. I can change the voltage and get different sizes, count them, and get the entire size distribution. This could be done in less than 1.5 minutes. Some of the newer instruments have fast scans. I can do it very rapidly, so I could do a dynamic measurement and see how my reactors are changing very rapidly with time. I want to control the processing conditions, so I can change the crystal phase and particle size. And TiO2 has two different crystal phases. This is a compact crystal phase. Rutile, it is more in a pigmentary application, has very effective light scattering properties, and this is what is in your sugar in your hotel room. This is more a very active catalyst, and we can then produce these things. So I just give you two examples. By controlling the quench rate, this is the rate at which I'm cooling down the gases at the exit of the flame. With a very high quench rate, I get what is known as the metastable crystal phase, anatase. This is the stable crystal phase, rutile. But by controlling this, if I suddenly quench it, I can sort of preserve the anatase peak and get a pure, this is a 100% anatase sample. Or I could play with the temperature gradient and get a mix of anatase and rutile. So these understanding then allows me to get different mixes of crystal phases, get highly pure crystal phases, again, depending on the application or depending on what I want to do with them later on. I could also obtain different particle sizes, and this is again particles that are collected. These are loose agglomerates. They're just piled onto the filter, and you can see there's a distribution. The geometric distribution is about 1.4, 1.38, and so forth. These are measured by electron microscopy, but I also have my online tool, and they tend to agree quite well. And these are, of course, a natural spread that I obtain for a given experiment. And I may not be happy with this broad distribution, relatively broad. In some sense, it's quite narrow in terms of the width, but I might want tighter control, and I might want smaller particle sizes. And you can see that the crystal phase, you can also determine it by X-ray diffraction. You can determine the crystal phase. You can see we make very tiny particles. And again, you can see the distribution of the size. And there is, of course, certain spread, but the mean size here is about 4.6 nanometers. Then we bring tools into play. My colleagues at Washington University have designed these tools. These basically bring in the aerosol, place a charge, use an electrical field. So it's called a multi-stage differential mobility analyzer. And what this allows me to do is very effectively charge the particles and then classify them and make them into a narrower size distribution. These are just some schematics of the pathway, but you can see I start with a geometric size distribution of 1.4, and I can bring it down to close to 1. 1, of course, means ideally monodisperse. And I can pull out different sizes at different stages and very rapidly get these nanomaterials which are very narrow in spread. And these are, of course, fabulous samples to have for all kinds of studies. So these are truly enablers because I want to eventually determine properties as a function of size. So with TiO2, you can now see I can end up with 22 different types of samples. I can keep the size about the same. Of course, some sizes are different here. And I can vary the crystal phase, different ratios, all by just playing with our reactors, different types of reactors and so forth. Or I can keep the crystal phase the same, anatase in this case, and vary the size from about 4 to 200 nanometers. So having these samples, then we like to collaborate. These are some ROS measurements that were done in Gunter's lab. So different size anatase, and here comes the metric. Now toxicologists typically use a certain mass concentration of the material. If I take the same mass concentration of 4 nanometers and 200 nanometers, obviously the surface area is way greater for the 4 nanometer material. So instead of doing it by mass, and you can also see there's no particular trend that comes out. Now if I do it with number, that seems to be some kind of trend, but very difficult to interpret. And now I normalize the ROS production per unit surface area, and maybe there seems to be a trend. And you can see now these small particles have a lower potential to produce ROS. Now very contrary to what people think, but this has been normalized by the surface area. The available surface area is so large that the active sites are actually lower per unit surface area. So we feel that this is a more representative measurement, and things like that need to be done before we can interpret effects of size and so forth. And again, this is repeated. Now we do the same with the crystal phase. If I just look at the ROS production, these are same size particles, mind you, but maybe the little difference in size. If, of course, the size is same and the mass concentration is same, these should be identical in terms of trend. But if the size is a little different, I can normalize it by the surface area, and you can begin to see amorphous now being quite active in this case. These are, of course, specific samples made, and anatase being next, and then, of course, rutile being the least. Again, the smaller sizes having lower ROS generation potential per unit surface area. So one can begin to pull these trends out and begin to compare things like that, and hopefully put and come up with some guidelines. I take it a step further, and we can make now composite materials. I'm not going to use pure TiO2. Of course, it's going to be mixed, and I told you it's used in your milk powder, but I also want to make composite materials. I want to dope the TiO2. Good material that we are now working with is copper-doped TiO2. We are hoping that it could be used to reduce carbon dioxide. It's a very energetic process to change carbon dioxide to a sort of lower oxidized state of carbon so that we can put it to some use. It requires a lot of energy. So if we could activate this by sunlight, you could use the light from the sun to activate this catalyst and then reduce CO2. If that works out, You can just imagine the amount of use that this would be put to, especially with climate change issues being addressed all the time. The process is very similar. I'm not going to walk you through it now. I bring in 2 precursors. I want to understand in great detail now what happens, and here are different pathways shown. I could get a coating depending on the pathway I go through. With the second precursor, I could completely coat my TiO2 particle or whatever particle that I'm making as the base. I could get islands of copper, or I could get a homogeneous mix. Again, processing conditions very readily allow us to prepare these things. And again, we've made platinum doped TiO2, palladium TiO2, platinum palladium TiO2. So you can play with all these things and come up with a whole mix of material. So here are some pictures of copper doped TiO2. Now, if you look very precisely, this copper is in an oxidized state. Here, of course, it's quite a bit of copper. The other interesting thing, you still don't see the crystal phase of copper oxide. So it's an amorphous state, but it begins to promote formation of the rutile phase. So under conditions, of course, we make pristine anatase TiO2. I begin to add copper. You can see that the rutile phase begins to appear. So one has to keep that in mind when one looks at activities and so forth. But very precise samples which can now again be put to functional use or toxicological tests and so forth. So we've been working with Gunter and his team and also bringing in certain instrumentation and delivery techniques and looking at this holistically. Of course, ideally, you would like to have some kind of toxicity ranking, TiO2 being very low in toxicity relatively, and things like copper, which are highly toxic, copper nanomaterials, and one has to do these holistic kind of tests, very detailed characterization to even have a hope of some kind of toxicity ranking, and of course, subject to what samples and materials are used. So we've been working, as I indicated, with Gunter's group for quite some time, and I think collaborations with groups, multidisciplinary groups, is probably essential to make any advance. Still a very complex thing. So I want to now go into the fate in aqueous environments, just to give you a snapshot, and I think I have a few more minutes. So we do make the best particles. Now this is keeping modesty aside, but what do I do about hard aggregates versus soft aggregates, and would these be important? Again, I can go back and make these materials, do the tests, and all kinds of different things. And eventually, what happens to particles, even when I'm doing a simple ROS measurement? I make these particles, throw it into a liquid, and I just give you, again, pardon me for the simple tutorial. Some of you haven't or forgot your chemistry. So I take a TiO2 material, just throw it in water, and hydroxyl groups attached to it. There is a certain equilibrium that is established. Now, this is clearly a surface area driven process, right? So you might think, oh, this is good for all TiO2, and I put it in water, I'm going to end up with a certain pH. As I'm going to show you very soon, depending on the size, the amount of hydrogen ions, the free hydrogen ions, which is of course a reflective of the pH, is going to be different, and you're going to end up with different pHs. If the pHs are different, the point of zero charge. Now, once this happens, the Ti and OH, depending on the pH in the system, also speciates into these two. This is a positive charged complex. So if I have a low pH, which means large amount of hydrogen ions, this is a preferred product. And at low pH, I'm going to have a positively charged TiO2 nanoparticle. Zeta potential is positive. If I have a high pH, low hydrogen ion concentration, the reverse, this is promoted, and I have a negative charged material. So the same TiO2 particle, depending on the suspension conditions, could either be positively charged or negatively charged. These are very important. And of course, if I'm close to point of zero charge, they're all going to agglomerate and settle out, right? So they're going to form very large flocks in the suspension. And of course, I can keep stirring it to keep them afloat, but they tend to form these flocks. So these are very important also for environmental studies, biological studies, and one can, of course, estimate the total surface charge depending on how much of each I have. The net gives me the net charge. So here are this is actual data now for all these samples. Only possible because we could make these materials very quickly, and you can see that the point of zero charge changes, and one can, of course, go through, and it all correlates to the total surface area now. So you can see as the surface area increases at low primary particle size, because of the large surface area, you're going to form more hydrogen ions, and the pH is low, and then the pH keeps increasing. So these are all very important, just a snapshot of some data that I wanted to show you. We also do, having all these samples, we collaborate with colleagues who put it to use in different environmental studies. I wanted to point like my colleague Jeremy Fine, who I'm actually seeing for the first time. So you don't really need to meet in groups. You can collaborate long distance, and he's done some very fabulous studies. And there is a poster out there which I encourage you to go and look. I just want to end now with our lab very quickly. 2 more minutes. I've been given the sign that time's up. So this is a sort of schematic of our laboratory where all these reactors are going. Here's a graduate student. Of course, you saw a picture of the hood, but the hood is not sufficient. And of course, maybe it's safe, but I really want to make sure as my student is handling all these materials that things are safe and we can do studies. The other advantage is that our instruments can be brought to bear. Things that we used to measure nanoparticles, I could now use as a monitor in the lab. These are different setups. I can go off design conditions. I can say that my hood is not functional, and you can see inside the hood during synthesis, this is the background concentration. The concentrations shoot up. I'm, of course, making nanoparticles in a flame environment, and you can see that if outside the hood, even if the door is left open because the hood is functioning well, the concentrations are very close to the background level. This is good, but good to know. But then you see that when you stop synthesis, firstly inside the hood, high concentrations. When you stop synthesis, there's a certain clearance time. Your graduate students or the worker shouldn't rush in to collect the powder. It takes a long time to clear out, even if the fan is on. Right here, of course, we were producing nanoparticles and the fan was left off. Then it doesn't drop, but if the fan is on, you can see it takes a certain amount of time. So these simple best practices are essential. And when I'm recovering particles, there tends to be a spike. You should do this in the hood with adequate protection and so forth. So with that, I will summarize, and you can read this. I'll come back to this. I want to thank the folks that fund us, our collaborators, for really working with us, which allows us to prepare all these fancy particles and put them to good use. So thank you for your attention.
Questions?
That was very interesting. So if you create these superacidic surfaces, I think that's what you're hinting, and now your particles agglomerate as during the settling time when you've told your students to stop the synthesis and things gel in the vial and you got them sitting in the vial, you've created this superacid. And so what happens then? Doesn't chemistry occur then in the presence of this acid catalyst in the surface, and you remodel the surface essentially because you've created now this super environment, and now you congealed it in a particle? Don't you have like shelf life issues or other things to worry about where that chemistry continues to evolve?
Yes.
Now with this agglomerated state that you've talked about.
Right. So yeah, this is a very good point, and especially if you have things like metallic dopants, you know, it tends to dissolve out. So you need to really do kinetic studies, or you need to have some kind of a coating which would protect and retain your nanomaterials. Now, so that these are very important in terms of the stability, shelf life, and things like that. Extremely important. And we oftentimes have techniques to preserve these materials and then come back a month later and recharacterize them, and oftentimes they're very different.
Yeah,
and then
that's the issue I've heard. A related issue, and I think it's a segue into Gunter's talk, but when you now have anatase in solution and you create hydrogen peroxide as your ROS, it's well known that anatase and hydrogen peroxide together are a nice catalyst combination that can oxidize alkenes. It can even oxidize glucose to gluconic acid. It's well known, even in the absence of light.
Right.
So the question is, now you've created this scenario where your very assay, creating superoxide or hydrogen peroxide with the anatase, now can do a third undesired or unobserved step
Yeah.
of creating toxicity in the cell that, in fact, the hydrogen peroxide was intended to measure, but in fact it's now being consumed to do an unauthorized oxidation in the cell. How do you get at the handle of the assay, the H2O2, and not consume it in a further step that's an oxidation that's going to contribute to cell toxicity?
Correct. So these are, of course, under very controlled conditions where you have developed a protocol to do the ROS measurements, but that's a very valid point, and one has to, of course, so somebody said let's not do in vivo tests, so they're complex, so you have to follow up with a sequence of tests which have been done with these materials. So you go from a simple ROS, which is non-cellular, then you want to do cell studies, then you want to do maybe an animal study, and if all of these correlate, then only do you probably have a good understanding. So very complex, and one needs to do that. Yeah.
More questions.
I was especially intrigued by your very, very last point, where you pointed out how you safely handle materials in your own lab. Since we are looking at ways of regulation and safe handling, also in the absence of very, very definite knowledge about thresholds and so forth, what do you think of the proposal that some people have made, the proposal that basically every scientific paper should include, along with the methods section, some kind of safety note which just simply records what safety measures were actually adopted in any given experimental situation, just to kind of set examples and, in some sense, share the stories?
Right. I think this is extremely important. And we, of course, brought in all our instruments to bear and wrote a paper on this thing so that at least the data is out there. So I think this would be very important, and our intent is to share. This is not driving regulations, or I'm not saying it's the ideal thing. It's a way of sharing best practices, right? So I think all of us need to do that, and I agree with you, and I would support it. Or maybe even if you have a lab going where you're dealing with a lot of nanomaterials, maybe stretch it a little further and publish that data and make it available. Very applied paper in some sense, but I think the best practices information is very important. Things like even in a hood, we know hoods are safe. We saw pictures yesterday, oh, this is very safe and so forth, but after you finish your processing, how long do you have to wait? What precautions? Of course, it's best to be precautionary all the time, which our students tend to do, but publishing some of these or making known the best practices or guidelines are very important. I know NIOSH is doing that too through some of their documents, and this is very important, I feel.
All right, let's thank Pratim again for excellent talk.